السلام عليكم ورحمة الله وبركاته. أهلا وسهلا فيكم في المحاضرة رقم 4 من كورس الباينفورماتكس. إن شاء الله اليوم حنتكلم عن موضوع مهم جدا وهو تكملة للموضوع السابق. في المحاضرة السابقة تكلمنا عن الألاينمنت أو sequence alignment والإيديت ديستانس، وهي مواضيع مهمة جدا في تحديد مسببات الأمراض. لما نقرأ الدي ان اي من شخصين، شخص سليم وشخص مصاب بمرض معين، واهم شيء يكون السبب في المرض جيناتيك، يعني السبب موجود في الدي ان اي، وبالتالي ممكن نستعمل خوارزميات الايديت ديستانس او السيكونس الاينمنت في تحديد الفروقات ما بين شخصين او ما بين سلسلتين من الدي ان اي. وبالتالي بنقوم بالمقارنات عن طريق خوارزمية edit distance مثلا أو الهامينج distance أو sequence alignment، ونقوم بتحديد الفروقات الموجودة ونوعيتها وعددها، ومنها من خلالها ممكن نتعرف على مسبب المرض، وبالتالي ممكن معالجته في مراحل في مراحلها الأولى، بدل مثلا نجرب علاجات، عدة علاجات ممكن ما تزبط معنا. وبالتالي بنساعد في عملية علاج المرضى وعلاج مناسب من غير تجربة أو من غير أخطاء معينة في الطب. مثلا نجرب أشياء ممكن ما تزبط على مرضى معينين، زي ما شفنا في قاعدة بيانات أوبن سناب. العلاج المناسب لازم يكون بيعتمد على التركيب الجيني للشخص في بعض الأمراض. آه، اليوم حنتعرف على موضوع له علاقة وبشدة بالموضوع المحاضرة السابقة، وهو اسمه Pre-Alignment Filtering. Pre يعني قبل أو ما يسبق الألاينمنت، وبالتالي معناها إنه هاي الخطوة بنقوم فيها قبل عملية الألاينمنت، وحنشوف ليش بالضبط إن شاء الله خلال المحاضرة. طبعا بأكد كمان مرة إنه الوضع صعب جدا في فلسطين بشكل عام، وإن شاء الله ربنا بيحميكم وبنصركم وبيقويكم بطعميكم بالدنيا وبالآخرة، وإن شاء الله شدة وبتزول قريبا جدا، تنتهي الحرب وبنرجع لحياتنا الطبيعية والدراسة بالجامعة، وإن شاء الله ربنا بيوفقكم تتخرجوا قريبا. كمان مرة الفيديوهات وكل المحاضرات وكل ما يتعلق بالمساق موجود على قناة اليوتيوب. طيب، شفنا في المحاضرة السابقة إنه الإيديت ديستانس أو الدايناميك بروجرامينج تيبل ممكن يكون كبير جدا. كبير جدا بيعتمد طبعا على طول السيكونس اللي بنستعمله في المقارنات. لو طول السيكونسز التو sequences we have very long two sequences, let's say 30K 30,000 مثلا طولهم، فبالتالي حكينا انه dynamic programming table ممكن ياخذ عندي حيز حوالي جيجا. ولو كان عندي طول السيكونسز 300K 300,000 character each of the two sequences, then the dynamic programming table would be around 90 gig. 90 gig is really huge, which is also practical. So it's very normal to get a length of about 300K for one of the sequencing technology, which is nanopore. We talked about it in the first lecture, where we have ONT devices or nanopore technology. Those devices normally generate read sequence ranges from 100 characters all the way to 2 million long character. So getting a sequence of 300K long, it's really usual. So normally the size of the dynamic programming table would be very, very large to handle. And we talked about multiple techniques that can reduce the size of the dynamic programming table, reduce the number of cells need to be calculated. We went through the banded alignment and adaptive banded alignment in detail, but also there are very efficient and more recent ways to do the exact same job, which is optimizing the number of calculated cells in the dynamic programming table. So the banded alignment would be the first way to optimize, but there are also recent algorithm called wavefront algorithm, or WFA, and there is the bidirectional wavefront algorithm, and there are many more algorithms that can reduce the number of calculated cells, as you can see over here. So now let's talk about one of the problems we will face in real world example in genomics. So think about, now you have two genomic sequences, and in reality, you will have really large number of those sequences, because we talked about getting sequencing reads from the sequencing machine, and then you have reference genome, which is really huge, very long, like 3 billion characters, right? Think about, you got a lot of pieces from the sequencing machine. Each of those pieces is 100 long characters. And then when you have 100 long characters and you'd like to find all the potential location where it maps to in the reference genome, that will give you a huge number of potential locations to use for the edit distance calculation. So when you have those pair of sequences, there are about 98% of the times that we are performing the dynamic programming table, we find out that the edit distance between those two sequences is way higher than the edit distance threshold, or than what we are looking for. So think about, we are looking for a disease that is caused by single edit operation. So we would set our edit distance threshold into 1, for example, or 2, right? But based on our observation, what we figure out is that about 98% of the times that we are comparing the two sequences using dynamic programming table, we find that the edit distance is still much greater than what we set as a threshold, which is 1. So you could find sequence pairs with error or edits, total number of edits of 2 or 3 or 10 or 20, right? So it's really waste of time that you build the dynamic programming table, you calculate the edit distance, and then you find it's much greater than what you are looking for. And then all the calculation you did, you just trash it, right? Because it's not needed for the application that you are working on. And if we have like million of sequence pairs, then you would build about million dynamic programming tables, right? And you wait until the very last cell until you figure out the total number of edit distance for each of those pair. And then you decide if those two sequences are similar to each other or not. But it's already too late, because you built the entire dynamic programming table. And then, as I said, you need to trash out all those calculations and you move on to the next sequence pair. So this is a real problem that we are facing in every day in genomics. And one of the solutions is basically to use what we call a pre-alignment filtering. So hopefully by now we agree that sequence alignment is very expensive to perform, and there is a huge workload to be computed, basically. And our goal is to accelerate any sequence aligner by reducing the need for dynamic programming algorithm. What does that mean? Let's see in the next few slides. Okay, so the basic idea of pre-alignment filtering is that you have genomic strings, you have genomic sequences, and we would like to categorize them into two types. So the two genomic sequences could be very similar to each other, or it could be totally dissimilar to each other, right? There is no other possible category. If they are dissimilar to each other, then just we need to ignore them, and if the number of differences exceeds a threshold. So this is how we define dissimilar sequences. If we have a threshold, which we call an edit distance threshold, and that is set based on the disease that we are looking for or based on the application. So normally we set it as 5% of the sequenced length. So if the sequenced length is about 100 characters, and we set the edit distance threshold to 5. but you can set it to 1 or 0 or 2 or to 3. It depends really on what you are looking for. And if that is your threshold, and then you find the number of differences or the edit distance between the two sequences to be 6 or 7, for example, which is exceeding the threshold, then we call the input two sequences as dissimilar sequences. However, if the number or the edit distance is or equals to the edit distance threshold or less than that, then we call them as similar sequences. And those are very useful, and we are looking for those sequence pairs. So in this case only, we would like to find the number, location, and type of differences. However, if they are dissimilar sequences, we don't want those information. So basically, we don't want to calculate the edit distance in this case. However, we want to calculate the edit distance only in those cases. So it would be very wise and very nice if we can find a way to detect those dissimilar sequences and just delete them without performing dynamic programming table. And this is what basically I mentioned in the previous slide, that we would like to find a mechanism to reduce the need for dynamic programming table. So we don't want to use the dynamic programming approach with dissimilar sequences, but we want to use it with only similar sequences. And we define the similarity or similar sequences to be those sequences that have an edit distance threshold equals or less than the edit distance threshold. So I hope this is clear. This is very important before we move forward. Okay. So to find a workaround or a solution to this problem, we propose what we call a pre-alignment filtering. So it's a filtering mechanism that filters the sequences based on their similarity before applying expensive dynamic programming approaches like edit distance algorithm or sequence alignment. So we have the two input sequences, right? And then we apply whatever filtering mechanism to them. And only if they are similar, we perform sequence alignment or any of the distance metrics that we studied in the last lecture. So that is basically the pre-alignment filtering. And to build a very successful pre-alignment filters, we need to satisfy 3 requirements. So the first one is to filter out most of incorrect alignment or most of incorrect or what we call dissimilar sequences. So we'd like to filter them out. And the second requirement is to preserve all the similar sequences. So we have dissimilar sequences, we have similar sequences. We want to basically to keep all the similar sequences, and would like to delete or remove all the dissimilar sequences. Remember, we cannot filter out all of the dissimilar sequences, but we aim to remove most of them. Because if we find a mechanism that accurately calculates the distance, then that is basically the dynamic programming based approach, because it is indeed the most accurate approach to calculate the edit distance. So we cannot basically find something more accurate than that unless it is really dynamic programming based approach. So that's why we are aiming to find most of them, delete them. However, we would like really to be very strict in keeping all the dissimilar sequences. The third requirement we have here is to do it quickly, basically, and that is the main goal behind pre-alignment filtering, right? So we have sequence alignment. Sequence alignment is very expensive to perform. There are a lot of number of cells that we need to calculate, and it's taking long time. So if we are taking the exact same time in pre-alignment filtering, then what is the main purpose of having an extra step before performing sequence alignment? All right, so let me delete the annotation. And now to quickly and reliably approximate the distance between two sequences without the need for dynamic programming algorithm, we are going to present the very first solution to this called Sneaky Snake, and then we will go to another solution called Grim Filter. There are many solutions that are proposed to address this issue currently. However, we'll go only through Sneaky Snake, which is still the most accurate pre-alignment filter in the literature and the fastest until today. So how we perform Sneaky Snake? So let's assume we have those two sequences. This is the first sequence, and this is the second sequence. And what we need to build something similar to the dynamic programming table, but we call it a maze. So M-A-Z-E. Okay, that is a maze. So what we have in this maze or in table is we pick one of the character from one sequence and we compare it to 2E plus 1 characters from the other sequence. So we pick one character from one sequence and we compare it to 2E plus 1 characters from the other sequence. And what we do with that is that we build the whole column from this maze. So assume we have here 0, 1, 2, 3, 4, 5, 6. That is the 6th character. And then what we do with the comparison that we have with the 6th character with those 2E plus 1 characters is that we are building the 6th column in this maze. So the corresponding character we have from the first sequence is going to tell us the index of the column that we have from the maze. What is the size of the maze? The size of the maze is, again, 2E plus 1 times the sequence length of the two sequences, or basically the first sequence. So the first sequence has a length of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is 12 character. And then the size of the maze would be 2E plus 1 times 12. So we have 2E. E here is the edit distance threshold. So it depends on what we are looking for. So think about the banded edit distance. We had a B over there, which is the exact same thing over here. So that is going to control the total number of edits that you can detect, which is the edit distance threshold, we call it in Sneaky Snake. So here it's a value that we can choose ourselves before we apply the algorithm. So in this example, I choose it as 3. So you can see here we have about 7 rows. 1, 2, 3, 4, 5, 6, 7. That is 7 rows. And we have 12 columns. And we said 7 is based on the equation 2E plus 1. The 12 is based on the length of the two sequences, or sequence 1, basically. Whatever is longest, then we consider it as the length or the total number of columns that we have in the maze. All right? So I hope that's clear. Now, how to fill or calculate or compute the table or the maze itself. Let's see. Let me calculate the annotation again. Now, since we are considering the 6th character, then we are focusing on the 6th column only. And what we do over there is that we compare the G with the G. So we have here 1 character, and then we go 3 characters to the right, 3 characters to the left, because 3 is our edit distance threshold. And we start from the left to the right, and then we start comparing the G with the G. If it is exactly matching, then we have the first cell in here as a white cell, And then we move to the next character, G and A. If they don't match, then we have a black cell. And then G and G, they match, they are exactly matched, right? So we have it as a white cell over there. And then the G and A, they don't match, right? So we have a black cell, and then G and G exactly matching each other. Then we have a white cell, and then the G and T, they don't match. So we have the black cell and another black cell. So the exact same thing we are doing to all the columns. For example, if we want to solve the third column over here. So if we want to pick the third column from here, so we go with the third character from the first sequence, and then we compare with the character, the opposite character or the corresponding character from the other sequence. And then we pick 3 characters from the left, 3 characters from the right. Here, we don't have 3 characters, right? So we have only 2 characters. So when we start with the missing character over here. And since we don't have any character, we assume it as a mismatch. So we directly fill that cell with the black cell because we don't have anything here, right? And then we compare the T with the G is a mismatch. So we have another black box, T and G, we have another black box, T and T, it's exactly match. So we have a white cell, T and G, they do not match. So we have a black box. And T and A, we have a black box again, T and G, that is also do not match. So we have a black box again. And this is how we calculate the third column. We do the same thing with the second, first, and all of them until we compute 7 times 12 table, okay? And that's what we call our maze that Sneaky Snake algorithm should work on, all right? So that is the first step in Sneaky Snake algorithm. Now let's move on. Now assume we build this maze, this entire thing, right? We build this black and white boxes based on the algorithm that we show in the previous slide. Now the Sneaky Snake, or this snake, the greedy one, what we'd like to do, we would like to move from the left side all the way to the right side. So the snake would like to pass from one point to the other point, from the source to the destination, and going through the path that has less number of black boxes. So basically the snake would like to find a horizontal path that has most likely the white boxes only. Let's see how. So the first step is to look horizontally in each row in the maze and like to count how many consecutive white cells we have in each row. So let's see. The first row, we don't have any, so that is 0. We don't have any white box, right? The second row, same thing, we don't have any white box, so that is also 0. The third row, we have only single, we don't have at all white boxes in the beginning. So that is also 0. In the fourth row, we have about 4 white cells or white boxes in the beginning, and that is giving us so far the largest number of white boxes in this path. If we move to the next row, we find only there is a single white cell. Here, 0. There are no white cells in the beginning of the row. So basically the snake cannot enter that row because we assume the black box is an obstacle. So it's blocking the way for the snake to cross in. The last row over here, we have a white box, which is available path. So the snake can come across it. However, we have about only single white cell. So when we look in overall in all rows, we find out that the optimal path for the snake is basically this way. Why? Because we have the largest number of white cells where the snake can cross in, right? So we have 0, 0, 0, 4, 1, 0, 1. And remember, we are counting the consecutive white cells in the beginning of each row, okay? Now, if we remove the annotation, you will see the number that we calculate, right? And we see we choose this path because it has the largest number of white cells, okay? Now we reach a black box at the end, which we consider an obstacle. And because we reach that after the path, then we calculate the approximated distance as 1, which we started as 0. And when we reach our obstacle in the same path, then we increase it by 1. Okay. Now we start over the exact same algorithm. So the snake will start at this stage from this column moving forward. So we start now calculating in this row, starting from here to the right side. Now in the first row, how many white cells we have in the beginning? 0, because the black box. Second row, same thing, black box. The third row, we have about 4 steps, right? So 1, 2, 3, and 4. And then the next one, we have 0. The next one, we have only 1 and 2 white cells. Here we have 0. Here we have 0. So based on the algorithm that we have in Sneaky Snake, the number or the path that we should choose is the one that has the largest number of white cells in the beginning of the row, which is this path. So now let's move forward. So we choose this path. Now we arrive into another obstacle at the end of the path. So we directly increase the number of approximated distance by 1, and now the number becomes 2. All right. So now we repeat the exact same thing. We start from here. We start from there because we have, this is the path, and we have an obstacle at the end, which we consider when we increase the number of approximated distance. That's why when we start with the column after the black box. This is very important for the correctness of the algorithm. Now we start again in the same iteration. We visit every row and start counting the beginning consecutive number of white cells. Here we have 0, none of the white cells. Here we have 1, we have 1, we have 0, we have 1, 0, and we have 0. And now it's really ties, right? So we have 3 rows with the exact same number of white cells. So how to break the ties? Basically, we can choose the first one. So if all of them exact same number, so we just choose the first one based on the algorithm or based on Sneaky Snake algorithm. So we choose this path. Let me move next. Yeah, we choose the first path. The next one, they have the exact same number of white cells, so it doesn't matter. So let's choose the first one. And because the path that we choose has a black box at the end, then we also increase the approximated distance by 1, and now it becomes 3. And then we arrive to our destination over here. So what is this telling us? So because the snake couldn't find a path that's full of white cells, it means that there are some obstacles, or what we call them edit operation. So because we have 3 paths, right, are caused by obstacles over here, and over here, then those obstacles are our edit operation. And that's why we consider them as the approximated edit distance. Now, this is a very fast way to calculate compared to the dynamic programming, because what we are doing here, we don't have any data dependencies. What is data dependencies? Data dependencies is that whenever you calculate any cell in the dynamic programming table, we were using the upper cell, the upper left, and the left cell to calculate that cell, which imposing some reordering or restriction on the way we calculate the dynamic programming table. Over there in the dynamic programming table, we cannot calculate randomly the cells. We have to follow column-wise or row-wise or anti-diagonal, as we discussed last time. But over here, as you can see, you can calculate any cell at any time. There is no data dependencies. You can calculate this cell by comparing the character over here in one sequence and the corresponding character from the other sequence. And that's giving you this cell directly without any dependencies. And that makes this algorithm really fast. What also makes it fast is that we don't really need to build the entire maze. What do we need to do, calculate? This is the only thing that we should calculate, is basically this shape that you can see in this table. So what's the difference between this and the previous slide? Is basically there are no cells calculated in this area, likewise in here, likewise in there, likewise in here. Why is that? Because remember, when the snakes start looking for a path, it visited row by row, right? One by one. So at this row, it's directly faced an obstacle, right? So there is no point of calculating the next cells because we are not going to choose this as a path since we don't have any white cells in the beginning. The same thing with the next row. If we directly face a black box, we stop calculating that row and we move to the next row. We stop calculating this row and we move to the next row. Here, we find 4 white cells, 1, 2, 3, and 4. And then we find the black box, so we stop calculating at this point. Then we move to the next row, we find it a white box, and then we continue because it's a white box, right? When we find the black box, we stop calculating at this point, and then we move to the next row. We find the black box over here, and then we stop calculating that row because we are not going to choose it as a path. We move to the next row, we find this is the white box. Then we continue calculating that row until we find the black box, we stop calculating. And this is how we apply sneaky snake in reality. Okay, and then we choose this path, we find the black box, and then we start over at this point. Let me highlight it in green. We start over in this point, and now the sneaky snake algorithm starts checking row by row. We see that this row has a black box, so we stop calculating here. We move to the next row, black box, stop calculating here. Next row, we find there are really 4 white boxes, so continue calculating the row until we find that black box. We stop calculating and we move to the next row. And this is how we save the calculation over here, and we build a very small, what we call a maze or a table for the sneaky snake algorithm. All right, so I hope this is pretty much clear with the animation. And now let's go back to the optimization that were applied to the dynamic programming table. So remember what we talked about wavefront algorithm, which is one of the state-of-the-art, very recent algorithm, very fast. And we have also the bidirectional wavefront algorithm. So those two, as you can see, build the minimal number of dynamic programming cells in the table. Now, in the results, we examine the benefits that we can get by using sneaky snake algorithm to accelerate sequence alignment. So how we use it is that we got, as we mentioned with the pre-alignment filtering, we got the 2 sequences, right? And then we have them as input to sneaky snake algorithm, right? And now when sneaky snake algorithm, it requires edit distance threshold. So let's say E equals to 3, as we have in the example in the previous slide, right? This is our edit distance threshold. Now, if sneaky snake calculate the approximated edit distance less than or equal the edit distance threshold, so that is the approximated edit distance. Let's call it AE as approximated edit distance, right? If it is less than or equal to 3, then it means the 2 sequences are similar to each other. And in this case, we need to perform edit distance algorithm to tell us where are those edit, how many, and what type of edit we have, right? So in this case, we apply the dynamic programming table. However, if we have another two sequences, right, we apply sneaky snake, and let's say sneaky snake takes the exact same edit distance threshold, so E equals 3, right? And then sneaky snake algorithm calculate the approximated distance as greater than 3. Then in this case, we don't need to apply edit distance, and we just ignore those two sequences. So we don't need to calculate the dynamic programming table in this case. And this is basically what we did in this experiment. So we said, let's take the fastest sequence alignment that we have, which is wavefront, right? And let's try wavefront alone and snake with wavefront. What does this mean? It means when sneaky snake says the two sequences are similar to each other, and then we use wavefront algorithm to calculate the number of edits, the type of edits, and their location, right? So what is the benefit of using pre-alignment with sequence alignment? Now, the execution time for wavefront, assume it as a 1 speed up. It means the total execution time of wavefront. And now when we apply sneaky snake before using wavefront, we can see about 5.5 of speed up. 5.5 faster performance compared to using wavefront alone. And as you can see in the x-axis is the sequence length. As we increase the sequence length, the benefits of using sneaky snake getting faster and faster. So at here we have about 9.6x faster performance by using sneaky snake combined with the sequence alignment. So pre-alignment filtering is very useful, very beneficial to accelerate the computation involved in sequence alignment. And this is not a surprise, as we explained in the previous slide. The sneaky snake algorithm has no data dependencies. So you can calculate the entire maze, the entire table, without waiting for the other cells, right? That is one of the benefits. The second benefit is that you don't really need to build the whole table. You need just to build a very small portion of it, depending on the number of white cells at the beginning of each row. All right. So there are other very important results in the paper. So I would suggest to go through the paper and check the acceleration speed up compared to the CPUs, FPGA, and GPU performance. And that makes sneaky snake the fastest and the most accurate pre-alignment filter until today. This is the paper. If you are interested, check it out, read it, and if you have any comments, I would be happy to answer it. All right, now let's move into a little bit different topic, and then we will go back to Grimm filter and continue with another example of pre-alignment filter. Here we are talking about data movement. So imagine you have a sequencing machine. It gives you a lot of reads, sequencing reads, right? You store them in the hard drive. And then whenever you want to calculate at a distance, what you should do is basically read or getting the reads from the hard drive into the main memory and then into the caches, and then try to perform at a distance in the CPU or in the processor. The problem with this model of computation, which is called the Neumann model. The Neumann model is where we have the memory or a hierarchy of memories where we store the data, and then we need to move it to the CPU to perform any calculation. This makes a lot of waste in terms of energy and calculation, because the communication medium between the hard drive, the main memory, and the CPU are bandwidth limited and power hungry. We're wasting a lot of energy in the system and taking a lot of time to move those data back and forth between different components. So what we said is that we really need to alleviate data movement bottlenecks. So we are moving the data from the sequencing machine to the hard drive, to the main memory, to the 3 level of caches all the way to the CPU. So what we did in this work is that we tried to accelerate sneaky snake algorithm, but we tried to accelerate it near the main memory. So we don't need the CPU to perform the calculation. How is that possible? There are new technology or new emerging FPGAs where they provide processing near the DRAM chip or the HBM memories. So in the DRAM chip, which is the main memory, right? In the FPGA, it provides an FPGA logic where you can do the calculation and you can shorten the trip between the DRAM and the FPGA. That is the traditional FPGA that we have, which is we use it as an example in the paper using AD9V3 FPGAs. There are also more recent FPGAs where we have the FPGA chip tightly coupled with HBM memory, which is high bandwidth memory. So this is we call a 3D stacked memory, where we have the several layer of DRAM stacked on top of each other, connected with short communication with the FPGA, where you can perform the calculation on the data in the same package. So we don't have off-chip communication. And that makes as if the CPU is inside the DRAM itself, which makes the trip shorter, make the energy less, the energy waste less, of course, and the calculation much faster because we have very capable FPGA and very high bandwidth memory where we can accommodate large amount of data. Can be in today FPGA is 80 gigabyte of data. So in this work, we try to use those two FPGA, and you can see a great speed up coming to the sneaky snake algorithm, which is about 27x faster performance using the FPGA and 133x more energy efficient compared to 16 core with 64 hardware threads, IBM Power 9 CPU compared to the CPU performance. So we're not going to discuss the details of the FPGA. That is just to give you a flavor on what are the things that we can do on acceleration, but this is not required basically. So this is just extra paper to give you more information about this topic. However, what is required from your side is the second, so sneaky snake plus gram filter. Now let's talk about gram filter, which is another pre-alignment filter using totally different mechanism or totally different algorithm. And this paper was published in 2018. What this paper trying to do, we are not trying to build a maze over here. What we are trying to build for each read sequence is what we call a bit vector, a bit vector. What we have in this bit vector, let me show you an example. So what we have in here is that we specify the length of the token. That should be an input from the user. So in this example, we have the token size as 5. What does that mean? It means we need to pick every 5 digits as one token, of course, overlapping digits like this. So we take 5, 5, which is very similar to the way we pick the k-mers, if you remember when we talk about minimizer seeds, for example. And here, this is the length of the k-mer, basically, which are 5 characters. And then what we would like to build is this bit vector. So it's a vector filled with bits. Could be 1 or 0. That's it, just 2 choices, either 1 or 0. So what is the length of this bit vector? So here we would like to enumerate all kind of k-mers that has a length of 5, regardless the input sequence that we are going to use. So we first need to enumerate all kind of k-mers of length 5, right? So we start from A, and then C, G, T, and then what we do next is A, and then C, right? Then what is next? A, C, G, and then A, C, T, right? And then we move on. So then we enumerate all those possible cases for all k-mers of length 5 until we reach T, which is 5 T's, right? And that would be the length of the bet vector, which is basically 4 times 4 times 4 times 4 times 4. Why? Because at each character, we have 4 possible options, either A, C, G, T. That is 4 characters, right? And then we repeat it 5 times, right? And we have a repetition over here. So we could enumerate with a repetition. So we could have A and A, right? In this case, it's basically 4 to the power of 5. 5 is variable, depends on the user, and the user choose token size or the k-mer size to be 5, right? But 4 is fixed. We cannot change it because there are always 4 alphabets in the DNA, right? A, C, G, T. So the length of the bit vector over here is basically 4 to the power 5, right? That is the length of this bit vector. Okay, so now how to fill this bit vector, how to calculate it? Should be 1 or 0, where are the 1s, where are the 0? What we do is that we go in the read itself and we get all the k-mers of length 5, all overlapping k-mers. Whenever we see a k-mer that appears here, we go and check where's the location of that k-mer in this list that we prepared. If it is here, we add 1 over there, right? And then we move next. So the next one is AAC. So where's AAC? Is this one. And then we add 1 in the bit vector, okay? And then we move to the next one, which is 3 A's, 2 C's. So assume there is 3 A's somewhere here, right? And then 2 C's, C. So we add 1 in the corresponding location in the bit vector. And then everything else in that bit vector should be filled with 0. And then what we will have this bit vector ready for us for that particular sequence, okay? So we build 1 bit vector per genomic sequence. So each genomic sequence should have a single bit vector, okay? And that is the meaning of each bit in the bit vector. So 1 means that token exists in the read sequence. And this 0 means the TTT never appears in that token or in that genomic sequence, okay? And now we would like to compare 2 sequences. So basically we calculate this bit vector for 1 sequence and this bit vector for another sequence. And then we compare the 2 bit vectors together to decide what is the approximated edit distance for the 2 input sequences. So how we can use a Grimm filter is the same way how we use sneaky snake. So we have 2 sequences, right? We use Grimm filter. We use a Grimm filter with input parameter coming from the user as a token size. Let's call it T, for example, which was 5 in the example, right? And then Grimm filter, we calculate for us approximated edit distance. And then if that approximated edit distance less than or equal the edit distance threshold, then we need to apply edit distance. If it is greater than the edit distance threshold, then we really don't need to calculate edit distance, as we explained several times. Now, the thing is how we calculate the approximated edit distance from the two bit vectors. And I will leave that to you as assignment. So please read the paper and try to figure out the equation on how we calculate if the two sequences or the two bit vectors that we calculate would give us approximated edit distance of 1, 2, 0, 3, 4. Let's see that. So one hint is that we really need to add the number of ones in one bit vector. Let's see in this example, 1, 2, 3, 4, 5. So we have 5 ones. And in here we have 1, 2, 3, 4, 5. So we have 5 ones. And then we do some comparison to these two so that we can approximate the approximated edit distance, or we can approximate the edit distance between the two sequences that we use to calculate the bit vectors. But I'll leave that, the details and the exact equation to calculate that as an assignment for you. All right. So there are some details about the implementation and hardware. So what we have in here, we have what we call HMC cube. HMC. So that is high bandwidth memory cube, where we have in one layer an FPGA layer or logic layer where you can implement the computation. So you don't really need CPU in this case. And then all other layers are basically DRAM layer. So they are main memory, full bank we have in here, or a full layer of banks, okay? So we have them stacked on top of each other on one package, and then we implement the gram filter in the logic layer where it can access the genomic sequences stored in each of the banks in the DRAM to get them, do the calculation in the logic layer, and provide the result directly. And it was very helpful since the gram filter has a bit vector structure that can be vertically laid out on those layers. So that provide a huge benefit and a huge bandwidth to accelerate the performance of a gram filter. We don't want to go through the details, so what I really need from your side is basically the algorithm behind the gram filter. And there are more details about how we implemented gram filter, but as I said, what you really need to study is the algorithm behind it. And this is the key results that we got out of the paper. If you're interested, please read out the paper. And that is basically what we have for today for pre-alignment filters. So very simple, very efficient, two algorithms that provide a great speed up to sequence alignment. So as a quiz for this week, we have 3 questions again. So the first question is that you need to apply sneak algorithm on the 2 sequences that you get from the previous quiz question, which is quiz number 2, question number 1, where you generated 2 sequences. One of them randomly using the tool, and the other one where you apply the edit operation that I mentioned in the quiz question. And you really need to calculate the approximated distance using sneak algorithm. And as a hint, you need to assume an appropriate edit distance threshold. Remember, I give you a certain number of edit operation. So your edit distance threshold should cover those edit operation. And based on the result that you would get, I ask you a question, is edit distance or dynamic programming based approach needed for this example? So think about sneak algorithm after you generate the results. Is the result less than or equal to the distance threshold or greater than value? And based on that, you can decide on the question. The second question, this is the assignment that I gave you. You need to check the paper, gram filter. I'm going to provide the PDF in the syllabus. And you need to figure out the equation used to calculate the approximated distance between the 2 sequences from their number of exist tokens. So think about that. We built the 2 bit vectors for the 2 sequences. Now, what is the next step? Now we have some 1s in the bit vector. You have some 0s, right? Scattered around the bit vector. We have some ones, we have some zeros, we have some ones, we have some zeros. Now, what is next? What is the equation to calculate the number of ones and compare them together to figure out what is the approximated distance? So you need to come up with that equation based on the paper. As a hint, you need to check some of the figures in the paper, and you will find it clearly mentioned in there. All right. So as a quiz, the third question in the quiz number 3 is, since now you figure out the solution to Gram filter or how it works, you need to apply it on the aforementioned 2 sequences that we use in the first question in this quiz, coming from quiz number 2, question number 1. Okay, and then calculate the approximated distance again, and compare your result with what you got from Sneaky Snake algorithm, and then answer this question. Is again edit distance or dynamic programming and based approach calculation needed here after the result of Gram filter? Again, what you need to do is to get the approximated distance from Gram filter, compare it with the edit distance threshold. If it is less than or equal, then we don't need dynamic programming. If it is greater than that, then we don't need dynamic programming. So if it is less than or equal to the threshold, we need dynamic programming. If it is greater than the threshold, we don't need dynamic programming. All right, I hope that is clear so far. So as a key conclusion, most speed up coming from parallelism enabled by novel architecture and algorithms. So we are focusing in this course on the algorithm or the algorithmic side. So we are always trying to study some algorithms that try to accelerate the performance of certain problems or certain solution. But there are also the other side of the course where we have hardware accelerator or hardware architecture that can accelerate the performance of the algorithm. As we can see in Sneaky Snake, we already developed some hardware architecture, either accelerated by HBM-based FPGAs or by having the 3D stacked memory as an HMC, for example. So if you want to get the best out of both sides, you really need to build efficient new algorithm and then try to accelerate it in hardware acceleration platform. If you want to prepare short video and get the bonus credit for that, I would recommend you to go to this paper, section number 7.2 on accelerating pre-alignment filtering, and try to check the other algorithms. There are Shuji, for example, Gatekeeper, and many more other algorithms that you can check the algorithmic side behind the paper, and try to prepare 5 minutes or very short video on that, and you'll get the bonus credit. Again, this is one of the best paper that you can study to give you more insights about the whole story of the course that we are giving, or the whole story of the algorithmic step that we are studying in this course. Thank you so much for watching. That's it. And I hope you enjoyed the course so far. And for any questions, yes, feel free to contact me directly, or you can write in the YouTube chat if you are watching us from outside the course. If you are enrolled in this course, please communicate through the WhatsApp group that we have. And thank you so much. See you next week.